Hi all, it's been a long time since the last time I've made one of these videos. I'm sorry about that. I had some technical issues, as they usually say, and some other concerns to deal with, so I haven't done anything. Anyway, so in the last video we talked about particle accelerators, so naturally in this one we're going to talk about particle detectors. Okay, so subatomic particles are tiny, so you cannot really see them through a microscope. Specifically, the nucleus is about 1 billion times smaller than hair, so that's really, really tiny. So the only way to detect particles is through the interactions they have with matter. And we have already seen one of these examples in the electron gun. So in the electron gun example, when an electron hits the fluorescent screen, green light is emitted. Emitted is with 2 M's, if I'm not mistaken. So anyway, so how does this happen? You can let me draw this and then I'm going to erase it. So you can imagine like you have a nucleus and an electron, say. Okay, this is a very simple atom, hydrogen. Okay, and then you have another electron coming in and hitting this electron. So what's going to happen to this electron? It's going to get promoted to a higher excited state. Okay, so it's going to jump to the next excited state. Okay, and then it will immediately go back by emitting a photon. Okay, this is something you have seen in the photoelectric effect probably. Okay, and that photon is going to have an energy of h, Planck's constant, times its frequency. Did I say electron? Photon. Okay, so, and this is what we see in a fluorescent screen. Okay, so the basic principle pretty much for detecting subatomic particles is ionization. Okay, let me erase this and I'm going to write it down. So the basic principle of detection is ionization. So what do you mean by that? Particles. And what do you mean by particles? Maybe it's electrons, maybe it's positrons, maybe it's nuclei, maybe it's protons, whatever. Anything that is of subatomic size interact with the atoms of a material, and more specifically its electrons, thus either promoting electrons to higher excited states or by ionizing atoms. Okay, and we've seen this already. So let's say that you have an atom with a positive nucleus. Let me erase this, sorry. Let's make it dashed. Okay, so this is supposed to be an atomic orbital. Okay, so maybe we have an electron here and we have an incoming electron coming with some speed. So maybe it will give this electron the atomic, this is an atomic electron. And this is an electron produced in an accelerator. Oops, sorry for my bad handwriting. Accelerator, I'm sorry. Okay, so maybe this electron is going to get promoted to the next excited state and then come back, or maybe this atomic electron will just leave the atom altogether. Okay, this is what ionization is, and this is the basic principle of particle detection. Okay, so once we accelerate some particles, in this case these electrons over here, okay, we have to make those electrons interact with some material, and that material is usually inside the detector, and that detector produces either light or current or some measurable effect that will tell us, okay, we have some radiation in this space, okay? So another thing I want to talk about before we dive deeper into some forms of detectors is the cascade effect, okay? Cascade effect. Okay. So what is that? So radiation, I have to fix this handwriting, I'm sorry. So radiation, so maybe it's alpha particles, beta, gamma, nuclei, whatever, ionizes a gas. So cascade effects are observed in gases, okay? So what do you mean by ionizing? The electrons of this gas get promoted to higher excited states or leave the atoms altogether, okay? So the radiation that comes into the detector ionizes the gas, and then you have secondary electrons produce ionization of other atoms inside the gas. Okay, so let's say that our gas is inside some tube, okay? So this is the tube, and it's filled with some gas. This tube is connected to some potential difference, okay? So maybe you have this potential difference, okay? This is the ground, and this is, since this is the positive side, this is the anode, okay? I mean, this side is the anode, and then maybe we close the circuit by connecting the negative side to the, let me see, did I mess up? Yeah, I did mess up, sorry. So let's make this clearer. So this is the anode, okay? The anode is a wire inside the gas, and this here, let's make it blue, okay? So this here is the cathode. So the cathode is connected to the walls of the cylinder, okay? This is not really important, but you can see that, let's say that we have some incoming radiation, and the radiation can penetrate the walls of the cylinder because, as we said in the beginning of this video, we're talking about something that is 1 billion times smaller than here. So with the spacing between atoms in the wall being of the order of magnitude of a few nanometers, I think, and the radiation having dimensions of 10 to the negative 15 meters, we see immediately that the radiation is 1 million times smaller than the walls of the cylinder, so it can penetrate the cylinder. Inside the cylinder we have some gas, say, okay, and electrons are produced, free electrons, okay, because they leave the atom, okay, they leave the atoms of the gas, okay. So these electrons are collected by, okay, the anode is positively charged, okay, so this is positively charged, so the electrons find their way to the cathode, and this produces a measurable current. And I haven't talked about cascade, about what cascade effect is. So let's say that we have, this is the atom of the gas, we have an incoming form of radiation kicking an electron out of that atom, and because this electron, the secondary, this is the secondary electron, okay, secondary electron, okay, this secondary electron is energetic enough to find, let's say that we had 2 electrons coming out, okay, so because these electrons are highly energetic, they find other atoms of the gas and they kick other electrons out of the atoms, and then these electrons find atoms of the gas and they kick other electrons out, and through this process we have this hole tube filled with electrons. Okay, so this is the cascade effect. Okay, this is something I wanted to talk about. Yeah, this is pretty much it as far as detection goes. Okay, so you have to make the radiation interact with the atoms of a material, exciting or kicking out electrons from the material, and then you have to find a way to gather that gather those electrons, and therefore you will know that okay, some radiation is in the space where I live or where I stay, whatever. But sometimes you need to go beyond detection. So beyond detection, which is another thing I want to talk about in this video. Sometimes we are interested in the type of radiation, and I'm talking about the initial radiation, so this one. Okay, so with this type of arrangement here, with this tube filled with gas, you can figure out that there is radiation, but whether this radiation is alpha, beta, gamma, nuclei, you cannot know, but sometimes you want to know. So sometimes you're interested in the type of radiation, that is alpha, beta, gamma, maybe it's an oxygen atom with an electron stripped out, maybe it's even uranium-235. You never know what kind of particle you will find. So 235 uranium. Okay, to be able to figure out the type of radiation, you need what is called bubble chambers or cloud chambers. So to find the type of radiation, you need bubble chambers or cloud chambers. This type of detectors, so this type, actually these type of detectors I forgot how to write, I'm sorry guys. So this type of detectors shows you the tracks left by radiation. So you can use a magnetic field. So you can use a magnetic field to decipher the type of radiation. So what I mean by that is that I'm gonna say this and then I'm gonna go back to the theory a little bit and then I'm gonna come back. So let's say that this is a bubble chamber, okay? And maybe you have an incoming positively charged proton, okay? So let's say that you have a magnetic field inside this bubble chamber that points into the page. Remember that when you have a circle and a cross, this tells you that we are seeing the back of an arrow that goes into the page. So the direction of the magnetic field is into the page. So how do we figure out the tracks of the proton once it enters, the track that the proton will take once it enters this magnetic field? We use Fleming's left-hand rule. So our index, I'm going to write it down, index is the direction of B, then middle finger is the velocity of the positively charged particle. So in our case, we are dealing with a proton which is positively charged, so that's okay. In case the charge was negative, you have to flip the direction of your middle finger, okay? So if I'm trying to say that If the charge is positive, then and the velocity is to the right, then your middle finger should point to the right. If the charge is negative and it travels to the right, you have to flip your middle finger and point to make it point to the left. So, but anyway, in our case, index is in, velocity is to the right. Therefore, the force, which is your thumb, so thumb is the force. Okay, so in our case, the force, we can easily see that it's up. So once it enters this space, it's gonna feel a force. Let's use green. That is up, therefore it's gonna bend this proton up. Therefore, you will know immediately that, okay, this is a positively charged particle. Okay, how do we know that it's a proton and not helium? We're gonna talk about that in a moment. Okay, so keep that thought for now. Okay, by the way, this can be a bubble chamber or a cloud chamber. Now, what's the difference between them? Okay, bubble chamber. Bubble chambers, let's use plural, bubble chambers contain a superheated liquid which is usually helium or hydrogen liquid. Okay, what do you mean by superheated liquid? Now you're probably puzzled. So when you boil water, when the water is at, say, 99 degrees Celsius, it starts boiling violently. Okay, so that's a superheated water. Okay, superheated liquid. Now, when it comes to helium and hydrogen, they are liquids when they are down to 4 degrees Kelvin, which is minus 269 degrees Celsius or lower. So they become superheated at very low temperatures. Okay, so bubble chambers, bubble chambers operate at really low temperatures. Okay, so bubble chambers contain a super heated liquid at the, what did I write there? At the verge. Okay, I'm trying to read my own notes, guys. So anyway, so the bubble chambers contain a superheated liquid at the verge of boiling. Okay, when radiation passes through them, it boils the liquid along its track. Okay, so along its track, forming bubbles. And these bubbles are visible by photographs which you can take, I guess. Okay, so this does not work for neutrons and gamma rays. And because this is a lesson and not a movie, I'm not gonna make it suspenseful for you. The reason is that neutrons and gamma rays are not charged, so they cannot interact with material, with liquid, so they cannot boil it. They cannot raise its temperature. Okay, let's now do cloud chambers. Okay, so the principle is the same. Radiation enters, leaves some tracks, and it exits. We use a photograph to see the tracks. It works for charged radiation only, so it does not work for neutrons and photons. But the principle of operation is that there is we use vapor that condensates into droplets due to ionization from radiation, making particle from radiation, comma, making particle tracks visible. So I'm gonna write here, it does not work for neutrons and gamma rays. Okay, so that's it about the principle of operation. Now remember when I said that in this example, okay, this one, how would we know that this is a proton and not, say, positively charged oxygen ion? Okay, simply by its mass. So I'm gonna write this down. The heavier the particle, so oops, the heavier the particle, the thicker the track it leaves inside the chamber, even for the same charge. For example, a proton and an oxygen 16 ion. Okay, so the oxygen 16 is heavier, occupies more space. As it goes through the gas, it's going to leave a thicker track. So let's visualize that. So let's say that we have, okay, so this is a chamber. For now, let's assume that there is no, actually, let me move this a little bit. Let's assume that there is no magnetic field. Okay, I found it, I was trying to say that. So let's say that we have a proton entering. Actually, let me use a different color. So we have a proton entering and a positron. Have we talked about positrons? I forgot now. But anyway, the mass of the proton is 1.67 times 10 to the negative 27 kilograms. The mass of the electron. Positrons are electrons that are positively charged, and they are the antiparticles of electrons. We're going to talk about them later. Now I remember how it goes. So the mass of one electron is 9.1 times 10 to the negative 31 kilograms. So we immediately see that this is about what 2,000 times lighter than protons. So when they enter the chamber, the track of the proton is going to be like this, like some thick line, whereas for the electron it's going to be a thin line. Okay, so this is the difference. Okay, let's write down why. Heavier particles carry more kinetic energy because kinetic energy is 1/2 mv squared. So immediately we see the mass there. Move slower, and interact with more atoms. As they pass through the chamber. Okay, let's go back to this example with the proton. Remember when we talked about using magnetic fields to bend the tracks of these charged particles? So let's go talk about magnetic fields. So magnetic, this is just going to be a reminder. So magnetic fields. So recall that let's say that okay, let me draw this. Okay, so we have a magnetic field we have a positively charged proton inside this magnetic field. So using Fleming's left-hand rule, so don't forget to use your left hand, by the way. So our index points into the page, our middle finger points to the right, therefore the force is up. So this is going to undergo a circular motion with the velocity tangent to the circle, okay? And this is going to be a circle with radius r, and the force is also always perpendicular to the velocity. So F is perpendicular to the velocity. Therefore, when this condition is met, we have circular motion. So F is m times v squared over r, where this is the angular acceleration. Remember, A is v squared over r. So let me erase that. Okay. Therefore, what is the force equal to? QVB is mv squared over r, and therefore this velocity cancels. So r is mv over bq. So if q increases, we see immediately that r decreases. So if q increases, r decreases. What else can we see? If mass increases, radius also increases, etc. So you can figure out lots of relationships from here, okay? So for a weaker magnetic field, we have a larger radius, which makes sense, right? Because if we have a really strong magnetic field, it's not going to bend it, it's going to bend it by a lot, okay? So it's going to have a smaller radius, and so on and so forth, okay? I'm not going to talk more about it. Let's go see some examples. And let me check my notes. We're gonna close with these examples, okay? So I tried to make this video short. So examples. So let's say that we have a chamber, we have a magnetic field into the page, okay? This is the magnetic field, and let's say that let's use red to draw an electron. So let's say we have an electron with velocity v going up, and we have a positron. We're going to talk about them, don't worry. Also with velocity v moving upwards as well, okay? So let's go use Fleming's left-hand rule for the electron, okay? So our thumb points into the direction of B, so into the page, okay? Now the velocity is up, therefore we put our middle finger to point up in the direction of the velocity. But remember that Fleming's left-hand rule only works for positive charges. This is a negative charge, so we flip our middle finger to point in the opposite direction of the velocity v. So our middle finger should point this way. So middle finger should point in this direction. I'm gonna erase that. Okay. So where's the force? My thumb points to the right, okay? So for this case, we're gonna have the particle moving. It's gonna experience a force to the right, which is gonna make it travel like this. Now, why does it spiral like that? Because as it moves through the chamber, it interacts with the material of the chamber, either the cloud chamber or the bubble chamber. It loses energy, and as it loses energy, the velocity gets smaller. Remember this formula here? If the velocity gets smaller, the radius gets smaller, which is what we observe over here. So the radius diminishes to 0 eventually, okay? Because it loses all of its energy inside the chamber. Okay, this is not always the case. Maybe it's so energetic that it doesn't lose that much energy, but you get the point. Now for the positron, again, Fleming's left-hand rule. In this case, our index finger points in, our middle finger points up in the same direction as the velocity, because this is a positively charged particle. Our thumb points to the left, so the force is to the left. So it's going to move to the left, it's going to lose energy, and it's going to spiral like that. So in opposite directions, okay? So I'm going to write this down. So since R is mv over bq, if the kinetic energy decreases, the velocity also decreases, and the radius also decreases. Okay, so this is what we observe here. Now let's go see another example before we close this video. So let's say that again we have some chamber with the magnetic field in as well. Okay, and then spontaneously out of nowhere we have this situation. So we have a point here and we get a spiral like that. Okay, and another spiral like that. Notice that I'm using the same colors as here, hinting towards the idea that this is an electron and this is a positron. And how did this happen? Remember when I said when we said that let's use yellow, photons and neutrons do not leave tracks inside the bubble chamber. So maybe a photon was coming in this direction. Okay, it was coming into this chamber. Okay, and at some point it was so energetic that it spontaneously decayed into a positron and an electron. We'll talk about that at some point. Okay, for now let's accept it. So for now, sorry, please just accept it. So since they are they have opposite charges, they move in opposite directions. Okay, so this is let's use black because it's not visible. So invisible photon, okay, decays into a positron and an electron. So this is called pair production, by the way. I'm going to write it up here. Pair production. Okay, and last example that I have here. And guys, please solve past papers. At some point, I'm going to get into those too. Let's say that we have this situation. Okay, so imagine we have a large chamber. Okay, and the magnetic field is into the page. Okay, now I have something coming in like that. Oops. Okay, let's say that I have something coming in like that, going out like that, and then here I have this picture again. Okay, so what happened here? All right, so this case is easy. This is pair production. So these two are probably an electron and a positron. Now the magnetic field is into the page. Okay, so you can decipher that here. Okay, since this particle has, I forgot to mention this, so we have something moving in this with velocity in this direction and something that moves with velocity in that direction. So if we use our thumb, our index finger pointing into the direction of B, and then let's put V in the let's put our middle finger in the same direction as this V. Okay, so this V. Okay, but if we do that, we see that there must be a force that is going to push this out, but we know that this is pushed in. Okay, so this is pushed in this direction. Therefore, we know that this is a negatively charged particle. Okay, and since this moves into this direction and it kind of spirals, so you can see that this guy kind of spirals like that. Okay, so we know that it experiences a force this way, and this guy experiences a force in that direction. Okay, so if we put our index finger in the direction of B and we put our middle finger in the direction of the velocity, we see that the force should be in this direction. Therefore, this particle that moves in this direction is also negative, okay, because it cannot be positive. If it was positive, it was gonna bend this way like this, okay, but it doesn't do that. Therefore, we know that this is also positively charged. Okay, so we have negatively charged. So we have a negatively charged particle coming into this point and going, and another negatively charged particle coming out of that point. And then at this point over here, we have a pair production. So how did this happen? Probably a photon or a neutron was emitted here. Okay, most probably a photon. Okay, which decayed into an electron and a positron, and that's the case for this diagram, for this example. And I'm gonna close up this video I forgot to say that, okay, this is a photon, okay, photon, which is a gamma ray, okay? And I'm gonna close this video by mentioning that in particle decays, which is something we're interested in. So in particle decays, comma, we have conservation of charge and mass / energy. Okay, we're going to talk more about that in the next video, but let's go see this example again. So in this example, this guy comes in, decays into something like that and something like that. Okay, so we have charge conservation. Why? Because we have a negatively charged particle coming in, a negatively charged particle going out, and a neutral particle going out. So charge is conserved. Okay, the same happens with mass, but we're going to talk about that in the next video. And this is all I wanted to talk about for particle detectors. Please like and share this video with your friends if you think it's useful. This is for the A-level test.